Okay, so today we're going to talk about momentum. So I've broken momentum into 2 days. Today we're going to talk about momentum and its conservation, as well as the biggest thing that we use momentum for, which is dealing with collisions. Tomorrow we'll talk about impulse, which will be a much shorter discussion. We won't do anything extra tomorrow. It'll just probably be a short talk because there's nothing else that really will fit in that slot super well. Momentum. Let's get into it. So let me actually back up. The big picture here of momentum, because I'm trying to make sure you have like the big idea, is that momentum is a conserved quantity and it's a vector, which makes it really good for predicting what happens when lots of objects interact with each other. Okay? That's why you should care. That's what makes it especially useful for things like collisions, because if I have objects that interact in a complex way, which collisions are complex, then I can normally predict what they're going to do by using momentum. That's the biggest thing. When we get to impulse, there's also like the impulse equation is just like a really powerful equation, but otherwise there's nothing super important conceptually. So let's get into it. I'll try to keep this as quick as possible. The basics of momentum here is that momentum is defined as mass times velocity. This is one of those things in physics that its mathematical definition is actually the best thing that we have, because there's not a very good conceptual definition. Really all the momentum is it's the product of mass and velocity, and it exists to be able to track moving objects. That's really all it is. It's a vector that represents an object's motion. That's it. That's all it is. There's nothing really special about it. There is no conceptual definition, right? Like with energy, we define it as like either, being the quantity that describes an object that's moving or has the potential to move. So it has like a conceptual thing. This one doesn't. It's just a math thing. But it's an extremely useful math thing, so it's important to know. One thing that you guys will want to know here is that the units are the kilogram meter per second, but you may also see Newton seconds. And in fact, Newton seconds are probably the preferred for a lot of people because it's easier to write and say. Those are algebraically equivalent. So you may recall, you probably don't, that a kilogram per meter second squared, a kilogram meter per second squared is a Newton. And so if I take that and multiply it by seconds, then one of those seconds on the bottom cancels out, and I'm left with a kilogram meter per second. So it's the same unit, just a different way to say it. Does that make any sense? There are no special shortenings here, like we saw like, hey, kilogram meter per second squared, that's too much stuff, let's call it a Newton. And then we saw the kilogram meter squared per second squared, that's too much to say, so we called it a joule. We don't have anything special here, we just keep it what it is. Does that make sense? Okay. Really important thing here is that momentum is a vector. It has a direction. That's incredibly important when we do all sorts of stuff. So let's put that into practice here. A couple of very quick examples. The first one, I have a running back who's running towards the goal line with a velocity of 8 meters per second. Let's call the line of scrimmage 0 and downfield positive. So if I'm running this direction as the running back, I'm running in the positive direction. So my velocity is going to be positive. When I multiply those values of mass and velocity, 100 times 8 is 800. So I've got 800 Newton seconds of momentum in the positive direction. And that's important that it's in the positive direction. Does that make sense? Here's another example. Let's say there's a linebacker that's trying to tackle me. So from the linebacker's perspective, they're moving this way. So their velocity is going to be negative. They're moving in the negative direction. Well, I still just multiply those two numbers. 112 times 5, well, that's going to give me what, 560? But it's negative, so it's a negative 560 Newton seconds of momentum. Does that make sense? The important takeaway here is that the direction matters, and just like everything else, in a one-dimensional sense, we use positive and negative for the direction. Are we comfortable with that? Okay. Now, what we're most concerned about with momentum is not the momentum of a single object, though you'll see with impulse tomorrow why that can be useful. What we more care about is the momentum of a system, because if I can monitor the momentum of a system, then I can make predictions. So let's look at how this works. Basically, you just add up all the momentum of each individual body, and that gives you the momentum of the system. Similar to what we would do with energy, but this time remember that momentum is a vector, so you have to be careful with like signs If you have two-dimensional problems, which y'all don't have to deal with in AP, but you might in the future, you have to think of those as two one-dimensional problems, just like with forces and with all that other stuff, right? Same idea. Let's look at a quick example. So let's look at that linebacker running back system. So we said before that the linebacker has 800 Newton seconds of momentum, and that was the running back. The linebacker has negative 560 Newton seconds of momentum, and so the momentum of the system is just the sum of the two. And since it's a one-dimensional situation, the vector sum is just adding the numbers together with the sign in place, which gives us a total momentum of positive 240 Newton seconds. Now what that would tell me conceptually is that even though each object is moving in opposite directions, the system as a whole is moving in the positive direction. Does that make any sense? Okay. Now where we really start getting interested in this kind of stuff is when we talk about conservation of momentum, because that's where I can start solving all sorts of problems. So to get the important information out there, momentum is a conserved quantity all the time, just like energy, right? And the reason we like these things is because if I can keep track of them, then I can solve problems with them, right? With energy, if energy was conserved, I can figure out, well, here's the different types, I can set them equal to each other, do all this kind of stuff. With momentum, we can do the same thing. Make sense? And here's how. Let's go back to that same example that we've talked about twice now with the running back and all the stupid stuff. Well, I'm actually going to pretend like we don't already know the momentum of the system, because it'll give me a better way to walk you through how to do this. There's a really simple statement that I can make that would mathematically express the conservation of momentum, and in fact, you can do it with anything that's conserved. The way that we could communicate this is we could say that the sigma, what does that word, that symbol mean?
The sum.
The sum. So I could say the sum, or the total momentum at the beginning is equal to the total momentum at the end, right? If momentum is conserved, this must be a true statement, so I can make it an equation. Make sense? So I could then dig into that, right? So if I have the running back and the linebacker, then I have two distinct objects, right? So before their collision, I could say that I've got the momentum of the running back at the initial plus the momentum of the linebacker at the initial. I've just unpacked that summation statement. Now, after they collide, we're told that the running back is firmly wrapped up by the linebacker. What I'm trying to communicate to you there is that for all intents and purposes, they become one object, right? They're going to collide, and he's going to hold them so tight that they might as well be one thing. And so that means that at the end, I could think of them as one and make it the momentum of the running back linebacker system. Does this make any sense? Now, that means each of these individually have got their mass and their velocity. And then at the end here, they're now one thing with a mass and a shared velocity. So I'm going to say that the mass then must be the total of the two. And they've got some shared velocity, which I'm just going to call v. Now what I've got here is a statement that I could easily solve for v. Does that make sense? And as we've already seen, I know all these numbers. In fact, I know that this total is a negative 240. And then to solve it, all I have to do is divide by their combined mass. And then I know what the velocity of that system is at the end. Does that make sense? Now here's what's interesting to see is that I would know from what I said before that I had a positive momentum this way, right? So after they collide, they're going to still have a positive momentum this way. That's what's interesting about the momentum of the system, is the momentum of the system, if it's a closed system, never changes. And you can see that here, right? If I have the system moving towards the goal line, it's going to continue to move towards the goal line. And there's nothing you can do to change that. Does that make any sense? Now, football, obviously, that's not the way it always plays out, because when you play football, you have interactions with the earth. And so you're trading momentum with the earth, and that makes things obviously different. But that's the basic idea with conservation and how you can use it. Does that make any sense? Lots of questions you can go back to using this idea, right? What's the momentum at the beginning? What's the momentum at the end? Make those into mathematical statements and solve that out. Another classic example is something like a father and daughter are stranded on the side of an ice skating rink, and the father pushes off so that he has a velocity of whatever, and you have to find the velocity of the girl, right? That's another example where at the beginning they have no momentum, and so at the end they would have two distinct momentums, so you get almost the opposite of this equation, but given enough information, you can work it out. So starting here and then unpacking what's happening at the beginning and the end is useful. Does that make any sense? Okay. All right. I think that's actually it for this presentation. Let's look at collisions. All right. So looking at collisions is probably the most common way that we apply momentum. In fact, this problem that we just looked at, that's a collision. So in AP Physics, you must understand that we tend to try and group into two different categories. However, those categories are really extreme ends on a spectrum. So when we start to talk about all this stuff, it's really important to understand these are extreme ends on a spectrum. So I'm going to give you a bit of a summary of what we're going to see here, and then we'll talk about it more intentionally. Let me grab a carbon track so that hopefully I can put it where the camera can see it. That'll work. Okay, so we will consider basically two types of collisions. The first one is what we call an inelastic collision, which is like this, where the two cars hit and they stick together and they fuse into one object. That's what we call an inelastic collision. That's what this was. On the other hand, the other end of the spectrum is an elastic collision, where the two objects hit and they bounce off of each other. Okay? But here's the deal. The way we define these, those are opposite ends of a spectrum, because what we will call a perfectly elastic collision is where all the mechanical energy is conserved, meaning I don't lose any mechanical energy, right? Like we've seen, if there's friction or whatever, some of that mechanical energy may become sound or heat or whatever. Not in this case. And you can tell that it's a perfectly elastic collision. I don't know why I can't speak. Because when they bounce together, there's literally no place that energy could have gone, right? Like, pay attention and listen closely, and what you'll hear the wheels, but you won't hear them actually collide, right? Like, there's no noise in the collision. They don't actually ever touch each other, if you look close enough. So that is what we call a perfectly elastic collision. The other extreme being a completely inelastic collision. And notice here, when they hit, you can hear them hit. So you know that I must be losing energy there. However, there's stuff in between where they will not stick together, so they'll bounce off, but there will be evidence that I've lost energy. Let me show you an example of that. So watch this. Like, they bounce off of each other, but did you hear them smack? That's evidence that I lost energy, or at least that I lost mechanical energy, because some of that energy made noise. So what AP expects to be able to do is kind of treat these two extremes, or idealize in these two extremes, while also understanding that there are collisions in the middle. Does that make sense? So the way you identify if it's one of those collisions in the middle is you look for some place that I would have lost mechanical energy, right? So those places will be things like sound production, heat production, or material deformation is also another one. Like, for example, car collisions. So most car collisions, they don't fuse together, so they're not inelastic the way we would consider them, at least not completely inelastic. So they bounce off of each other, but there's clear evidence that energy, let me say it again, mechanical energy was lost. Because the materials deform, there's heat created, there's clearly a lot of sound, right? There's all sorts of these things I can tell. So, important to understand, the vast majority of collisions in the real world fall somewhere between the ends of that spectrum, and AP expects you to be able to work with the ends while understanding there is stuff in the middle, and know how to determine when a collision is not one of those perfect ones. Does that make any sense? That's AP for you. All right. So, getting into the ideal ends here, we'll come back to impulse tomorrow. Like I said, we categorize them into two types, elastic and inelastic. Really, the best way to say these is, you may have noticed that I fumble with my words a little bit, because I always just shorten it to elastic and inelastic, but the best way to say it is that we have a completely completely inelastic collision, meaning that they stick together 100%, they don't bounce. And then we have a perfectly elastic collision. Oh, I said the wrong thing again. Back up. So, perfectly elastic collision means that energy is perfectly conserved. Completely inelastic means that they completely join together. So, you may see those words tacked on, you may not. In general, I just shortened it out to elastic and inelastic because that's too many words. All right, so let's talk inelastic collisions. This is what we saw here. Okay, so in this case, we'll see two different objects that they collide, they fuse together, and so the mathematical analysis will always follow this same pattern. We'll always start with two distinct objects at the beginning, becoming one object at the end, and so we'll always get a mathematical statement like this. Now, important to understand, momentum is always conserved, and that leads to one mathematical statement. Now, in this case, notice that if I know all the initial conditions, this leaves me with one unknown, right? I would just not know the velocity, and that's it. And so one equation, one unknown, that's solvable, no big deal. Does that make sense? Please note, this equation is not on your formula sheet. You don't get to have this. You're going to have to start from scratch every time and say, all right, well, momentum's conserved, so all of it to the beginning is equal to all of it to the end. I have two distinct objects with their own momentum. I've got one object with its own momentum, and then I can express each of those and then solve that equation. That's what they expect you to be able to do, is start from that core principle and work it out every time. Does that make sense? Okay. Elastic collisions are the ones that are a real pain in the butt. All right, they suck. Nobody likes them. The reason for that is because if you start with this principle, so let me just say, all right, I've got two objects that bounce off of each other. If I start with this principle, then I've got two objects that each have their own momentum at the beginning. But then at the end, when I look over here, I have a bit of a problem in that I have two unknowns here. I can't solve one equation with two unknowns. That's like basic algebra, right? I can't solve that. But that's where we get lucky with elastic collisions, that we have this second thing that I know. So the second thing that I know is that mechanical energy is conserved. So I can make another similar statement and say that all of the mechanical energy at the beginning is equal to all of the mechanical energy at the end, right? Each of these objects has its own kinetic energy. So to save board space, I'm going to jump straight to that and say, well, then I've got 1/2 m1 v1 naught squared plus 1/2 m2 v2 naught squared. This is each object's individual kinetic energy. Has to be equal to each object's kinetic energy at the end. Now at this point, I have two equations with the same two unknowns. So now I've got a solvable situation, but this would be a linear quadratic system, and those really suck. Like, nobody wants to solve a linear quadratic system. This is where if you know how to do it, you can let your school bus calculator, that's what I call these yellow ones by the way, you can let your school bus calculator solve this for you. There's a way to make those things solve a system of equations for you, so it's not that big of a deal. But it kind of sucks. And again, we're not getting any of these statements on our formula sheet, so you've got to be able to build them from scratch. I will tell you though, so here's what we get is these equations. I will tell you though, there is a bit of a shortcut equation. So every year what I will do is I will take these two equations and I'll use algebra to smush them together and give me a third equation that's easier to use. Okay? But again, you have to memorize it. So it's in the slides. It's this bottom equation here. I don't have time to show you all the algebra of how we get there, but basically you like rearrange each equation and then you divide the equations by each other, a bunch of stuff cancels out, and you're left with that. What's up?
So you just cancel out the m's?
No. It's a lot more complicated than that, but the m's do cancel out. What you do is you move all the one stuff to one side, the two stuff to the other side. You then factor out the m's on the top equation. On the bottom one, you move, ones on one side, two on the other side, but then what you're left with is a difference of squares, which you then factor out. So you factor out the m's, you factor out the difference of squares, and then you divide them by each other, and a bunch of stuff cancels out, and you get that equation at the end. And then you group them ones on one, initials on one side, finals on the other. You don't need to know all that though. You just need to know you can use these two equations to solve an elastic collision, and you're gonna have to memorize that bottom equation if you want to use it. Okay? It's not necessary though, especially if you figure out how to get the calculator to solve the complex system of equations for you. Make sense? Questions, comments, concerns? Okay, so generally that's how we do our collisions. That's the entire collisions thing. I will tell you that I have seen AP get a little bit extra sneaky, and so I want to give you a little bit of a heads up here on something. So remember, the idea is that mechanical energy is conserved in an elastic collision. What I have seen them do is something like this, where they take the track the cars are on and they tilt it. So that now you have to either use work for the carts, or you have to use potential energy to deal with their energy changes. So don't be shocked if something like that happens on like a free response question or something like that. I've only seen it one time, and I think it ended up being hard. I think it ended up being harder than I thought it would be, because when it comes to their momentum, you also have to now calculate their impulse, because the Earth is now interacting in a way. But anyways, that might be a thing. I don't know. Just keep your head on a swivel. You never know what physics is going to do to you. Right, Alyssa?
Right.
Thank you. Okay, so that's it. So to summarize, momentum is P equals mv. It's a vector. It's conserved. Because it's conserved, I can use it to solve all sorts of problems. Chief among those problems is how to deal with collisions, because collisions are really complex interactions that I can't really understand very well, except by using momentum. That's where it really starts to make more sense. And you have two types of collisions you'll see. Elastic collisions, where the two things bounce off of each other, and inelastic collisions where they stick together, right? When we look at elastic collisions, momentum and mechanical energy are both conserved, and so you can get two mathematical statements out of those ideas and then solve that system. If they stick together in an inelastic collision, then only momentum is conserved, but that's enough information to solve one equation based off of that idea. Does that make any sense? That's basically it. You just got all of collisions, which is like 2 weeks in, like 20 minutes? About 25 minutes. So there you go. Now you know. We just leaving whenever we want now? I'm just kidding. That's actually preferred. I
It's
just
actually the word.
felt like I wanted to be mean to you. What? Bye. Any other questions? Okay, that's it.
Momentum.